Now that you have learned about different types of data and ways in which it may be collected, we will continue our discussion and focus on analyzing our data. Descriptive statistics are the most commonly used type of statistics encountered by health information technicians. We will talk about measures of central tendency and measures of variability. Measures of central tendency and measures of variability are used to describe frequency distributions. The measures of central tendency may look familiar. They include the mean, median, and mode. Over the next several slides, we will define these terms and give you a couple of examples of how they are calculated. It is important to understand the meaning of these terms when you are analyzing your data. The first term we are going to discuss is the mean. You have been calculating the mean of your data since you have been in grade school. Instead of mean, you may have called it the average. For example, let's say you've had 5 tests in your biology class and you received a 61, a 94, a 90, and a 95 on each of your last tests. To determine the mean, you would add up the scores you received on all your tests and divide that number by the total number of tests you took. The score adds up to 435 points, and you would divide that number by 5 because that's how many tests you took. The mean, or average, would be 87. Hospitals calculate the average length of stay the same way. However, hospitals would be working with hundreds or thousands of patients per year instead of 5 as in our example. In our example, John, Jane, and Tom each stayed in the hospital for 3 days. Sam stayed 6 days and Mary stayed 5 days before being discharged. We would add up each of the patient's length of stay for a total of 20 days. We would divide that number by our total number of patients. 20 divided by 5 is 4. Our mean, or average length of stay for this data set is 4 days. In this example, we are going to use the same data set, our test scores. However, this time we are going to calculate the median for our data instead of the mean. To calculate the median, we do not have to add up the scores. We simply have to put them in order from lowest to highest. We would report all scores even if there is a duplicate. Next, we find the middle number. Since we have 5 scores, our middle number would be the third number. 94 is the middle number. There are 2 scores lower than 94 and 2 scores higher than 94. For our test scores, 94 would be the median. This is much higher than the mean for the data set. Our mean was 87. To calculate the median for our 5 patients, we would use the same process. We put the lengths of stay of all 5 patients in order from the shortest length of stay to the longest. Next, we find the middle number. Again, we have 5 values. The third number is our middle number. Our median is 3 for this example. We have 2 numbers to the left and 2 numbers to the right of our median. Our median is 3, and our mean for this group of patients was 4 days. This is closer than our test score example, and we will talk about why that is a little later. The mode is the number reported the most often in the data set. Our data set is our test scores. We simply find which, if any, score occurred more often than any other score. In this example, we scored a 95 twice, and we scored a 61, a 94, and a 90 just 1 time each. Therefore, 95 is our mode because it is the number reported the most often in our data set. For our patient's length of stay, 3 is our mode because it was reported more often than any other number. 3 of our patients stayed 3 days, while 1 patient stayed 6 days and 1 patient stayed just 5 days. As you can see, mean, mode, and median may or may not be the same for your data set. It is possible for your data to be skewed. If you have a value that is either very high or very low, your mean may be distorted. If you have one value that is way out there, either much higher or much lower than the other values, this is called an outlier. because it does not really represent the norm. This happened with our test scores. This student did very well on 4 of the 5 tests, receiving a 90% or better on 4 of the tests. However, the first test score was only a 61. This skewed the mean. It really pulled down the student's average. Of course, the opposite could also happen. Let's see how a higher value could skew the mean. This is our same 5 patients. However, this time, John Smith's length of stay in the hospital was 30 days, not 3 days as previously reported. The higher value will skew the data. If we recalculate the mean, we would add up the 5 values. By adding up the length of stay for our 5 patients, we came up with 47. We divide this total by the number of patients. 47 divided by 5 equals 9.4 days. Remember, in our original example, John's length of stay was 3 days and our mean was 4 days. Notice how all of our other patients only stayed between 3 and 6 days. Their length of stay is closer to the 4 days than it was the 9.4. John's long length of stay skewed or distorted our mean, and our data really does not reflect how long patients typically stay in our facility. Now that you know that a very high or a very low value can skew the mean, let's see if a very high or a very low value impacts the dataset's median. As you recall, to find the median, we put all of the values in order from lowest to highest. Once they are in order, we simply find the number in the middle. There was a slight rise in the median. It went from 3 to 5. However, if we had a lot of data, more than just 5 patients to report, there would likely be no change in the median. This time, we are going to see if one very high or very low value impacts the dataset's mode. The mode is the most commonly reported value. In both sets of data, more patients stayed 3 days than any other of the lengths of stay reported. The mode did not change. It remained at 3, even though one patient stayed for an entire month. Another important term you should know when reporting your data is range. Range is a little different. To calculate the range of your data, all you need to do is subtract the lowest number in your data set from the highest number. For example, if all the students in a kindergarten class were ages 4, 5, or 6 years old, their range would be 2, because all the children fall within a 2-year range. Subtract the lowest age from the oldest age, or 6 minus 4 to get your range. The age range of a college course will be a lot wider. You may have students ranging in age from 16 to 80 years old in a college course. If this is the case, the range would be 64. I subtracted 16 from 80. Let's look at the range for our length of stay data. The first set of data was a range of 3. We subtracted the lowest value from the highest value, or 6 minus 3. The range for our second data set is much larger. The range is 27. We have calculated this by subtracting our lowest number from our highest number, 30 minus 3 to get 27 for our range. Remember, to find the range, the largest number minus the smaller number. It is very easy to calculate, but there are a few disadvantages. Only the highest and lowest numbers are taken into account. As you can see, an outlier can really influence the range of your data. John Smith's very long length of stay in the second example really changed our range. Since outliers can really have an impact, it may be better to calculate the variance of your data. The variance will show you how far each of your numbers are from the average. To do this, you would subtract the mean of the frequency distribution from each value in the distribution. The difference is squared. The squared differences are summed and divided by n minus 1. This equation looks very complicated, but it really isn't that bad. Let's take a look at our formula first. Once you know what the symbols mean, you just replace them with your own data. we will calculate the variance of our first set of data. Our patients for our first set of data are listed in the first column. Their lengths of stay are listed in the next column. The mean or average length of stay for this group is 4. The mean is listed in column 3. In our equation, we are to subtract the mean from each patient's length of stay. For John Smith, it would subtract 3 minus 4 to get -1. We do this for every patient. This will show us how far away each patient's length of stay is from the mean. For example, John Smith's length of stay is 1 day less than the mean or the average. We take each of those numbers and square it. We multiply it times itself. For John Smith, it would be -1 times -1, which equals 1. Sam Green's would be his length of stay, or 6 days, minus the mean, and this equals 2. His length of stay is 2 days greater than the average. Once we square it, we come up with 4. After this is done for every patient, we add them all together, because we must get the sum of all these numbers to get our top number in our equation. We add them all together, and we came up with 9 for our numerator. To get our denominator, we always use 1 less than the total number in our population. We have 5 patients, so by subtracting 1 from that number, 4 will be our denominator. We find our variance by dividing 9 by 4, and we come up with 2.25. This is our variance. Now we will calculate the variance for our second set of data. Remember, the only difference is John Smith's length of stay was 30 days instead of 3, which increased our mean to 9.4 days. This outlier also had a huge impact on the range of our data. Again, we have added our data to the table and calculated the numerator. We go through the same steps and subtract the mean from each of the patient's length of stay. The negative number means that they fall under the average. In this example, 4 of the 5 patients' length of stay were below the mean. This is because John's 30-day stay really inflated our mean. Our mean really didn't reflect the average length of stay for most of our patients. Next, we squared the number and totaled them. Our sum is 537.2. This is our numerator. Our denominator is the same. We always just use 1 less than the total number in our population. Since we have 5 patients, our denominator is 4. In this example, our numerator is much higher because our patients' length of stay are a lot further away from our mean. By dividing 537.2 by 4, we find we have a variance of 134.3. The higher the number, the further our data is from the mean, which means that we have too much variation in our process. The variation is used to determine the standard deviation. You may remember the term standard deviation from one of our earlier modules. The standard deviation will show how the values in a range are distributed around the mean. This may sound confusing, but it really isn't as bad as it sounds. As you may recall, in performance improvement, it is important that the process or performance does not have a lot of variation. You do not want to deviate too far from your mean. Remember, the mean is your average. If the average wait time in your emergency room is 40 minutes, you don't want your patients waiting anywhere from 5 minutes all the way up to 2 hours. If your average wait time remained at 40 minutes, it would be better if the time your patients were waiting ranged from like 32 to 45 minutes instead. Of course, it would be even better if the overall average wait time decreased. If you could reduce the average wait time to even 30 minutes while maintaining very little variation from the average, that would be an improvement. With a 30-minute average wait time, and with the times ranging only from 26 to 33 minutes, You may have fewer angry patients. Hospitals apply the same logic to lengths of stay for their patients with similar diagnoses or surgeries to determine if they are operating as efficiently as possible. Now that we know the variance for our two sets of data, finding the standard deviation is easy. All you need to do is find the square root of the variance. For our first data set, our variance was 2.25. The square root of 2.25 is 1.5. We will see the importance of this a little later. For our second data set, our variance was 134.3. The square root for our variance is approximately 11.6, which means our data deviates a lot more from our mean than it did in our first example. As you might have guessed, we do not want our data to have a lot of variation. We do not want our data to be too far away from our mean. The terms on the next few slides are important to know when analyzing your data. When plotting out your data, you will want to see how it is distributed. If it has a normal distribution, it means that your data is symmetrical, with 50% of your observations above the mean and 50% below the mean. The mean, median, and mode will be equal. This is called a bell-shaped curve because of the way it looks. The base of the curve is your range. It is better to have a narrow base, meaning the range is smaller. A perfect normal distribution has zero skew. This slide indicates how many observations fall within a certain range of the mean. The areas under the curve corresponding to 1, 2, and 3 standard deviations are 68.3%, 95.4%, and 99.7%. Let's take a look at how our first set of data will look once we plot it out. Our second set of data was skewed. It looks more like this. There are other ways to look at your data. If a customer requirement is 9 days, an average of 7 looks pretty good. But if we focus solely on averages, we forget all about the people that required 9 days. These are all unhappy customers. The idea of Six Sigma is to decrease the number of unhappy customers when you decrease the variation and narrow the curve. By decreasing the variation, our average remained at 7 days, but the number of customers who missed the 9-day requirement was decreased by a lot. This will result in having fewer customers who are upset with your service. As we have seen, your data will not always have a normal distribution or have a bell-shaped curve. Oftentimes, your data has outliers or the data is not evenly distributed. When this happens, it is said that your data is skewed. It is not symmetrical around the mean. It may be asymmetrical, and it can be skewed either to the left or to the right. The mean is sensitive to extreme observations. The mean moves in the direction of the long tail when a distribution is skewed. When the direction of the tail is off to the right, the distribution is positively skewed, or skewed to the right. When the direction of the tail is off to the left, the distribution is negatively skewed, or skewed to the left. Data that is skewed to the right isn't necessarily better than negatively skewed data. It just indicates how the data is distributed. If the data is skewed, the shape of the curve will not be symmetrical. Take a look at how the mode, median, and mean are affected by skewed data. If the mean, median, and mode are close, but not exact, it would not be considered to be significantly skewed. How do you think our data in our two length of stay data sets would be distributed? Normal or skewed, either to the left or to the right? This example shows how minimizing variability can improve quality. The dark line shows the baseline performance. The data is skewed to the right. We can tell that there is a lot of variability in the process because the base of the curve is wide, indicating a broad range. The targeted performance is displayed with a lighter line. The process was really tightened up with not a lot of variation in the process. The base of the curve was narrowed, which will make the curve higher because more observations are recorded within this smaller range. The targeted shape is a bell-shaped curve, meaning mode, mean, and median are all the same.